Differential equations were in section 3.1, day 4. We are revisiting electrical circuits. Now, the first time you saw electrical circuits, it was in section 1.3. We even had a video on 1.3 where we just introduced some basic terminology. Back then, you would just set up a differential equation. Today, we're going to set it up, but we're going to go one step further. We're actually going to solve it. So, a couple of things to remember. Current. Well, current is usually represented by the letter I, the variable I. It's measured in amperes. Resistance. Resistance usually looks like a sawtooth. It's R for ohms. Inductance. Inductance, you can see a coil, usually like a little spiral right here. That's measured in henries. Electromotive force. That's represented by E in volts. Capacitance, that's C. Those are measured in farads. C usually will be designated with two parallel bars there. And then a charge, Q, is in coulombs. So let's take a look at our first scenario, an RL circuit. We have a resistor. And we have an inductor. We have inductance and resistance. So what we're always going to do is link into a voltage drop. So with R, V equals I times R. Current times resistance. That's going to be a voltage drop. And that's what you have for that very famous formula. Inductance, L. Remember, inductance is a property, to generate an electromotive force as current changes. So V is going to equal L times di dt. That's that change in current. And I'll tell you what you do in this regard. And if you always think about this, it's going to be very, very helpful. You can just say, well, let's deal with these voltage drops. When we look right here, we'd have L times di dt. And we could say, well, there's another voltage drop from the resistor. We could say plus I times R. Well, that should equal the total voltage that we have right here. That's E. So, guys, right now, believe it or not, you're basically done. What you do is you divide by L, which is a constant. And when you do that, you are going to see very quickly that you arrive right here. So this is your very famous RL circuit. My suggestion is, however, to think about it in terms of voltage drops, set it up that way, and it makes a lot more sense as you write and form the differential equation. Likewise, we could have an RC circuit. We could have a resistor, and we can have a capacitor. So as we're looking right here, we could do the exact same thing. We could say, well, let's take care of a voltage drop for the resistor. Well, V equals I times R. We could say, well, let's look at the voltage drop for the capacitor. Well, that would be Q divided by C. So that right there is something that we haven't talked about recently, but it could be very, very helpful, and it will be very helpful as we set up these equations. So the capacitor, you take Q, a charge at a particular time, divided by C. That's how much your voltage will drop. Well, add these up. We could say, well, we'd have I times R plus, well, Q over C is equal to E. Now, right now, as you're looking at this, you're going to notice that, first of all, you don't even have a differential equation. And you don't seem to see reoccurring variables. But this is where we get to another very, very, very important definition, that current is really a rate of change. You can think of it that way. It's how the charge electric charge changes with respect to time. And if we were to use that, then we could say, well, here's our dq dt times r plus q all over c equals E. Now what? Divide by r. And when you divide by r, well, I think it's only going to take you a moment to see what's happening here. You're going to get this equation that we have right here. What's the benefit of it? Well, I'll tell you. It's a differential equation with respect to q here. You're taking dq dt. Q is in there. You're solving for q. So let's jump in and do one example together. It says a 12-volt battery is connected to a series circuit in which the inductance is 1/2 Henry and the resistance is 10 ohms. So determine the current I if the initial current is 0. So this is an initial value problem. They're saying initial current. That means when time is 0, the current is 0. And, let's go ahead and draw ourselves a little, circuit here. We're going to have an inductor. We're going to have this resistor. And, our flow, our current's coming this way. We could say, hey, we're going to start with a 12-volt battery. That's going to be our E. And it's connected to this series circuit. The inductance is 1/2 of a Henry. That's going to be, of course, a constant. L is equal to 1/2. A resistance is equal to 10 ohms. So we can write 10 here. By the way, the ohm looks something like so usually. And then we could say, well, can we deal with some voltage drops? Well, remember what we said before. With inductance, it's L times di dt. Inductance generates a voltage drop as current changes, and that's coming from that equation right there. Of course, for resistance, we have V is equal to I times R. So if we were to very quickly set this up and put in our constants. Let's see, we've got a 1/2 di dt. This is a 10 right here, so we'd have 10 times I. Our E is 12. And if we multiplied everything by 2, you could see very quickly you come up with this nice differential equation. Now, back in Chapter 1, you would stop right here and you'd say, well, there it is. There's my differential equation model. Right now, however, we'd like to solve. And the cool thing is we get to review something that's ongoing, really, that we need to know for the entire year. Solving such a simple equation like this, you might remember the integrating factor from our recent chapter. We're going to say our integrating factor is E up here to the 20. Well, our independent variable is T, and this is going to be E to the 20T. So how did we deal with this integrating factor? Well, you know what? We multiplied everything in this differential equation by E to the 20T. Here, I'll even put this after the 20 here. Even the right side gets multiplied by E to the 20T. And then you look at this left-hand side, and it's the product rule. And we can write it, actually, as saying, you know what? It's the derivative of E to the 20T times I. And from here, wow, we are really moving. We're doing a good job. We're going to integrate the left side and the right side with respect to T. This left side, because we wrote it as a product rule. It's going to work out especially nice. It's just e to the 20t times I. And this right side, well, we've got to reverse the chain rule, don't we? So we're going to go 24 all over 20 e to the 20t plus some constant. And 24 over 20, I think we all know, is going to reduce rather quickly. We're going to get dividing out of 4, 6/5. So that's going to work out pretty nice and fast. Tell you what, solving for I, we can divide everything by e to the 20t, including the constant, by the way. And just like that, you're going to be able to have, here, let's bring this back over here. We'll have I is equal to just a 6/5. Let's bring this up as e to the negative 20t. So, hey, we've solved very nicely. It's just that we need to remember that when t is equal to 0, I is equal to 0. You might remember that was our initial current, right? And so we can have 0 is equal to 6/5 plus c e to the 0, which is just a 1. So c equals negative 6/5. And our final answer, very nicely, this is going to be our equation of current with respect to time. So we can plug in whatever t value we would like, and we'll be able to find the current at that particular time.